Well, thanks for the invitation to come speak here. So I guess I want to start off with a very large goal, an overarching goal for this whole program, and it's classify foliations up to birational equivalence. I mean, to birational equivalence. And to do that, well, first off, we want to associate to every foliation a fundamental invariant, namely its canonical class. So Carolina defined this for us, but just to refresh our memories. So definition, given a foliation, we define the canonical class K of F to be minus the first Chern class of the tangent bundle of, or tangent sheaf of F. And it turns out, to realize this goal, I think, taking a hint from the classical story, a good idea is to try and make KF as neff as possible. As neff as possible. And I guess recall that say a divisor is neff, so a Q-Cartier divisor D is neff if D dotted with C is non-negative for all curves contained inside X. And here, I guess, we'll take X to be projective. OK, so part of what I want to convince you of today is, even if you don't care about classification, which, I mean, maybe you don't, I want to try and convince you that this is still a good idea for lots of different problems, that there are lots of different things that this kind of philosophy can be applied to. And hopefully I'll convince some of you to try and take up these tools too, to your own problems. So let's, so I want to recall something that Enrique talked about, I guess, last week. And I want to recall, well, how we make KF as neff as possible in the surface case. So let's let X be a smooth projective surface. And let's let F be a one-dimensional foliation. So we're going to make make KF. So we're going to make KF neff by running a foliation MMP. And so I'll describe how this is supposed to work. OK, so yeah, here's how we do it. So let's start off. So I guess we have a smooth projective surface. So X is smooth, dimension 2. And with F, we're going to start off F having simple singularities, or Seidenberg type singularities. This is just some, mild class of foliation singularities. It's kind of the nicest class of foliation singularities, maybe. And we start off, we ask ourselves, well, is KF neff? So this should look kind of familiar to what Carolina was talking about a few days ago. If the answer is yes, then we stop. We have a minimal model. So F is a minimal model. I guess I should mention while I'm up here that this is a bunch of work from Brunella, Mendez, and McQuillan. So yeah, OK, so if KF is neff, then we stop. There's nothing to do. We have a minimal model. Otherwise, there exists a contraction. So there exists a morphism phi from x down to y, which only contracts kf negative curves tangent to the foliation. So you should think that we're just modifying the foliation somehow leaf-wise, or somehow we're trying to run a relative MMP over the leaf space of the foliation, whatever that means. Okay, so we have this contraction, and there are two possibilities. Well, either the dimension of y is less than 2, which is the dimension of x, and we stop. Here we have a Mori fiber, what's called a Mori fiber space. Or the dimension of y is equal to the dimension of x, and phi is a birational contraction, so it'll just contract a single curve tangent to the foliation. And then we go back to start in this case. Okay, and the point is that each time we run through this diagram, the Picard rank of the surface decreases by 1, so eventually this process has to terminate in either a minimal model or a Mori fiber space. Okay, I should mention a small subtlety, is that in this case, y, when we contract the curve, y might actually be singular. But it only has cyclic quotient singularities, so it's a very mild singularity. And so it's not too much of a cheat to say we just go back to start. So this is just for surfaces. My goal, so for today, what I want to talk about is, can we generalize this picture, or generalize this diagram, to the case where the dimension of x is 3, and the codimension of f is 1, or dimension of f is 2. And as Carolina pointed out, I guess on Wednesday, somehow threefold geometry, running the MMP, or trying to run the MMP in the category of threefolds, is actually quite a bit more subtle. And there's some interesting new features of threefold geometry. So I'll just go back and kind of point out where things are wrong. Well, so let's start off with x is smooth threefold now. F codimension 1 with simple singularities. And we just start, and we say, OK, well, is kf nef? If yes, we stop. If no, we can still produce a contraction. If the dimension of y is less than 3, then we're in a Mori fiber space. But if the dimension, dimension of y is equal to the dimension of x, we have this new possibility. So there are two cases. Either the exceptional locus of phi is a divisor, in which case, so we're either contracting a divisor down to a point, or maybe we're contracting a divisor down to a curve. In either case, I mean, we acquire singularities that are worse than simple singularities on a smooth variety, but somehow, the singularities aren't too bad. So aren't too bad, and we go back to start in this case. And return to start. But there's something really weird that can happen, right? That the exceptional locus of phi could be a curve. So in other words, we're just contracting some curve in the threefold down to a point. And as Carolina explained to us in this case, the singularity on y now, so y acquires just singularities which are too egregious to continue. So y has a really bad singularity. In fact, so if we denote g to just be the push forward of the foliation f on from x onto y, that in fact that k of g isn't Q Cartier in this case. And so we can't go back to start because, well, we can't even ask the first question in our MMP anymore. You know, the notion of, you know, kg being nef doesn't make any sense. So we have to do something else in this case. And I mean, that'll be a foliation flip. What I want to do is I want to write up an example of a foliation flip, just to show that one, this actually really does happen, and two, I think if we look at this example and kind of squint our eyes, we'll sort of see how to produce foliation flips in general, and what the general strategy for both producing foliation flips is and the general strategy for showing that they terminate. So, okay. So here's the example. I'll say just at the start, the underlying map between spaces is just going to be the Atiyah flop. But when we put the foliations on top of it, it'll become a foliation flip. Okay, so let's let Q just be a quadric, you know, sitting inside P3, and let's let Y inside P4 be the cone over Q. Okay, and let's let G be the foliation on Y, which is the cone over the foliation on Q induced by the projection onto the first coordinate. Onto the first coordinate. So, you know, just about pi1 across pi1, or p1 down to p1. Okay. So now let's let D1, or let's let DI be the, so I guess DI will be a divisor inside Y, be the cone over a fiber of the ith projection. On Q, and we're going to let X, as Caroline explained, be the blow-up of, I guess I want to take D1 inside Y. Okay, so now I want to draw a picture of what this all looks like, roughly. Yes, we're blowing up a Vey divisor inside Y. Yeah. So if here's Y, so Y is some cone with some foliation, and the foliation has a bunch of leaves going through the vertex, or you know, the closures of leaves going through the vertex. The blow up X, so we'll call it phi, is just going to extract a single rational curve. We'll call it C. So this is X. And let's let F be the transformed foliation. Now the leaves of this foliation are just going to be a bunch of planes passing through C. So it's going to look something like, I mean, it's a dicritical foliation with a bunch of leaves all passing through this rational curve C. And we can compute, and it's not too hard, that we can compute that F dotted with C is equal to -2. So our only option, if we were to come across this situation in the MMP, which, I mean, we've just made it, our only option is to contract C down to a point, but we can also compute that Kg is not Q Cartier. So how do we fix this? Well, let's blow up the other divisor and see what happens. So let's let x plus be the blow up of d2 inside y. And again, this blow up, so we'll call this map phi plus. This map also extracts a single rational curve. But now the curve is going to be everywhere transverse to the foliation. So the leaves are just going to be, disks meeting this curve C at a point, or each at a point. And we can compute that kf plus, so we'll call this curve C plus, kf plus dotted with C plus is equal to 2. Okay, so what we should do then, what this diagram tells us, is that if we come across the situation, if we want to make kf more nef, we should actually replace x by x plus. So we should perform a flip. So we'll let f be our flip. So this is our foliation flip. Okay. So I want to make a few sort of silly remarks about this picture. Well, okay, the first remark maybe isn't so silly, but it's quasi-silly, I guess. Notice that there exist exactly two, well, okay, so notice that everything is toric. And there exist exactly two torus and F invariant divisors on X. So we'll call them S1 and S2. We know that the pair, and what we can compute is that Kx plus S1 plus S2 dotted with C is also minus 2. And the pair X S1 plus S2 is in fact log canonical. The second remark is that F plus is smooth. So what I want you to think is that the flip improved the singularities of the foliation. So okay. So with this example in hand, I want to state the first main theorem I have. Or in some sense, the central main theorem, I guess. So this theorem, I guess, is comes from some working collaboration with both Paolo Cascini and Roberto Svaldi. So theorem, so and myself, and then myself and Roberto Svaldi, which says the following. So let's let X be a smooth projective threefold. And let's let F be a foliation, a codimension 1 foliation with simple singularities. Then there exists a sequence of divisorial contractions and flips. So starting from X, F, so X, oops, F0, we have a bunch of birational maps which terminate in some new foliated variety, such that one of two things happens. Either so KFN is nef, or there exists a map, call it phi, from xn down to some space z, such that the fibers of phi are tangent to Fn and are Kfn negative. So it's a Morey fiber space situation. Okay. So in other words, I mean, this is the MMP for threefold foliations. And this is what we're able to prove. So I want to give a quick proof sketch about how we prove this. I mean, by kind of pointing to this picture and waving my hands a lot. But yeah, so if we end up in the Morey fiber space situation, then yeah, through every point of x there is I guess there's a rational curve passing through it which is tangent to the foliation. Yeah, codimensional. Yeah, so yeah, I guess I should say that Michael McQuillan has some work on this problem in the one-dimensional situation, or when f is dimension 1. So yeah, I guess yeah, if you want to run an MMP for pretty much anything on a threefold now, you can do it, which is pretty cool. Okay, so yeah, so the hard part is showing existence and termination of flips. So this is somehow the most challenging part of running this whole program. So let's talk about existence for a second. Well, the idea with existence is, let's say we have a flipping curve. So let's C be a flipping curve. So by this I just mean a curve which is contracted. It's the only curve which gets contracted by one of our contractions that we're trying to do. And let's let SI be the collection of all leaves slash Safartrices meeting C. Well, what we'd really like to do, so we want to realize the KF flip as a KX plus the sum of the SI flip. But this makes no sense, right? I mean, the SIs are just these crazy analytic, immersed manifolds. Maybe some of the SIs are even formal, if it's just a formal Safartrice of a Safartrix of like a saddle node. So these things are probably totally garbage. But the trick is we're actually able to approximate all these SIs. So by using Artin approximation. Sorry?
What kind of approximation?
Artin approximation?
Artin?
Yeah, Artin. I guess actually we use some stronger version by Elkic. So by Artin Elkic approximation, we can find I guess algebraic divisors SI tilde approximating the SI. Okay, I mean, there's a slight subtlety here that we have to maybe do we actually pass to some Attal neighborhood of C. So maybe there's a bit of fiddliness here, but we can pretend that we can approximate these by algebraic divisors on so I guess approximate the SI near C. And now, and I guess we can check two things. We can check that KX plus the sum of the SI twiddles dotted with C is negative. But we can also check that X and this boundary is log canonical near C. Okay, and so in that case, what we do is we've reduced the KF flip to a KX flip, or to a log flip. So reduced KF flip to a log flip. And we're on a threefold, so we know that log canonical flips exist. Okay, so this is existence. Basically, again, the idea is to, like we saw in this example up here, is to reduce the foliation flip to some kind of log flip. Okay, so for termination. Termination, I guess, is a bit of a thornier issue. I think it's a bit harder to prove, but I think it's conceptually very simple why termination should happen. So like I said, in our example, we saw that termination, or flips, improve singularities. So remember, flips improve singularities. And so what you can observe is actually, so after a finite sequence of flips, every flipping curve will be disjoint from the singular locus of the foliation. So be disjoint from sing F. And what you can show then next, after a while, you don't touch the singular locus of the foliation. So I guess this is actually really, it's a version of special termination for foliations. But then what you can show is that if a flipping curve is disjoint from sing F, it's actually KX negative. So I guess I'll call our flipping curve C. So if it's disjoint from sing F, then in fact KX dotted with C is negative. So what's going to happen is we're going to do a big line of foliation flips. And then at some point, our foliation flip is also a KX flip. And so termination follows because, well, threefold flips terminate. And so holds because, I guess, I'll call it classical threefold termination holds. And then we're done. So again, to repeat, the two main ingredients are basically just to reduce things as much as possible to the KX situation. So flips, we reduce via some approximation argument to constructing log flips. And termination follows from a combination of a foliated version of special termination together with the fact that threefold flips terminate. Okay. So I want to make a quick remark, or, well, a few, I guess, quasi-technical remarks. Okay, the first one is that we can work with pairs of a foliation and a boundary. So we also don't need to start with x smooth, and f having simple singularities. We can even start with something mildly singular. And then finally, we can also do all this works in the relative situation. Okay, cool. So maybe I want to put forth just a quick comment slash question, which I don't know the answer to. Oops. There we go. Maybe I want to leave this up for a sec. Okay, so question. Can we do this in the log canonical setting? So this is one thing I don't know how to do. I don't know how to work. So if f is log canonical, and I'll do a refresher on what this means in a second. If f is log canonical, does this work? Or can we run the MMP? I mean, from what Carolina's explained to us, if we want to use any of these ideas to study fauna foliations, I mean, fauna foliations are always log canonical. They're never just canonical. So if we want to study fauna foliations using the techniques of the MMP, this question needs to be answered. I don't know how to do it, so needed if we want to work on fauna foliations. So f has simple singularities. Yeah. I guess I should say that really we can start off with an analog of DLT for foliations. So this all works. This is okay for a foliated version of DLT. So yeah. Okay, cool. So what I want to explain now is how we can apply this theorem to things which aren't the classification problem. So I want to start off by explaining an application of this whole circle of ideas that Roberto and I have been working on to sort of hyperbolicity problems on foliations. Okay. So application. So I just want to again recall the definition of log canonical for foliation that Carolina explained to us. So definition. So I'm going to start off. So let x and f be a foliation on some variety, not necessarily smooth. And let's let pi from x twiddle to x be a birational modification, or birational morphism. And let so we have a foliation f, and then we have a transformed foliation f twiddle upstairs. So we can write kf twiddle is equal to the pullback of kf plus the sum ai ei, where the ei's are the pi exceptional divisors. And we say that f is log canonical if ai is bigger than or equal to negative epsilon EI for all birational modifications and all exceptional divisors. And recall that epsilon of a divisor E, this is just 0 if E is invariant and 1 otherwise. So I guess in the classical setting, when your foliations is the whole tangent sheaf, no exceptional divisor is invariant, and so this just reduces to the classical definition of log canonical. Okay. So now we say that a Z inside, so a subvariety Z inside X is a log canonical center, or just LC center, if there exists a pi, so a birational modification X tilde and X, and an EI, as in that diagram, such that pi of EI is equal to Z, and AI is equal to negative epsilon of EI. So in other words, it's it's just a place on the variety where the singularities are as bad as possible. Okay. So I want to give a few examples. I mean, so this maybe is a bit abstruse, but it's really these things are actually should be pretty familiar to us. So so remark is that every strata of a simple singularity is a log canonical center. So of a simple singularity is an LC center. And that's just easy to compute because you can compute the discrepancy of the blowup at an LC center pretty easily. Or sorry, the strata of a simple singularity easily. Another remark is, I guess this well, maybe it doesn't exactly follow from how I've set things up, but this is still true, is that invariant divisors are LC centers. Because I guess somehow you should think of invariant divisors as showing always with coefficient 0 in all these formulas anyway, so they're always LC centers. Okay, so with these ingredients, we're able to prove the following statement, which I think is pretty interesting. So theorem. So this is myself and Roberto Svaldi, and it's a foliated analog of a result that Roberto proved a few years ago. So maybe it's from 2015, 14. Okay, so yeah, a few years ago. So here's the statement. So let's let X be a projective threefold. And let's let F, and well, I'm going to throw in a boundary now, but still, again, this is still an interesting statement, even without a boundary. Well, maybe, okay, I'll just figure out the boundary for the moment. F is log canonical, but you should have in the back of your mind there's a boundary here, if you want it. Log canonical. And suppose there does not exist a map S from, so an algebraic map S into X minus the union of all, so the union of all LC centers. So does not exist one of these things. And tangent to F and also that there does not exist a map S1 from A1 into W minus, okay, I'll say W in a second, minus the LC centers contained in W, and where W itself is an LC center. And the conclusion is that, so if we don't have any of these A1s, then KF is NEF. So maybe I want to reformulate this slightly in a more, sorry? Oh yeah, sorry, yeah, this one, yeah, tangent to F, thanks. Yeah, thank you. Okay, so I mean, maybe another way of seeing what this theorem is saying is that so remark. What this is saying is somehow if there's so if KF plus delta, or if KF is not NEF, and somehow the leaves of, or and somehow the LC center, and so I guess, and somehow, and all invariant divisors are hyperbolic in some sense. I mean, I'll put quotes there. Then there exists an A1 sitting inside our foliation at some point. So then there exists a map from A1 into X minus the invariant divisors. Minus, somehow the singular locus of F. So we can cook up A1s inside our variety. Okay, so which I guess maybe touches on one of the questions that Jarek was asking. Yeah, so if there's any negativity to KF, then there somehow must be an A1 sitting inside our variety in some way. And in such a way that it doesn't touch the singular locus of the foliation or any of the invariant divisors. So I think this is actually a kind of strong statement about how this A1 can be sitting inside our variety. Okay. So maybe I want to say a few words about the proof, because I think the proof, I think, is a consequence, or the main ingredient of proof, I think, is of a statement which is somehow, I think, of independent interest. So the way we prove it is by using a foliated version of the connectedness principle. So connectedness. And so what this says is it says something about LC centers of weak phono-foliations. So let's let X be a projective threefold, and let's let X down to Y be, well, maybe I'll state in the absolute case, but then explain how to do this in the relative case. So X is a projective threefold. F is a codimension 1 foliation. And let's say that minus KF is big and Neff. So it's a weak log font of foliation. Then the union of all the LC centers of our foliation F is actually connected. So then the union of all LC centers of F is connected. Okay, so like I said, I think this is somehow of independent interest. It's a bit curious. Yeah, thanks. F to be log canonical. Yeah. So again, yeah. I mean, part of what I want to convince you is that maybe this terminology of using LC centers is again maybe a bit weird and foreign, but really, I mean, it's really saying a rather down-to-earth statement about the geometry of foliations. So I guess to make a quick remark about this is saying that if in this situation, I mean, here's just a stupid consequence, is that if there exist two components, let's say two disjoint components of sing F. So let's just say that let's assume for the moment that F has simple singularities. And if there exist two disjoint components of sing F, and minus KF is big and Neff, well, then by connectedness, I mean, if they're disjoint, they must be connected by some LC center. The only LC center that connects them has to be an invariant divisor. So there must be an invariant divisor containing both of these components of the singular locus. So divisor containing both of these components. But this is just like one sample application of the sort of statements you get, and it's a rather curious geometric flavor. Okay, so taking for granted foliation connectedness, I want to explain how we produce this A1 inside our variety. Okay, so the way we produce the A1 is by running an MMP. Okay, so let's just suppose for simplicity that, so to go, just to recall where we are, we're in the setting of trying to prove this theorem right here. So let's just suppose that minus KF, or KF is not Neff, and suppose that KF restricted to any LC center is Neff, where let's see, center. Our goal now, so our goal is to produce an A1 tangent to F. Yeah, that's a fair point. Yeah, I guess. So I guess what I want, I just want to rule out dealing with this case right now. So I guess somehow we want to rule out this case, and you can kind of handle it philosophically in the same way. So I want to show that if KF isn't Neff, then we're producing a map from A1 into X minus the union of all the LC centers. Okay. So as KF plus delta isn't Neff, we start running the MMP. Or KF isn't Neff, there exists a contraction phi from X down to Y. Now, what we can show is we can show two things. We can show that every fiber of phi is a tree of rational curves. And what we can also show is, well, by the connectedness principle, so by foliation connectedness, we know that by definition and the fact that KF is, or minus KF is phi ample, we see that every fiber of phi meets the non-KLT locus, or the log canonical centers, in at most one point. So that each fiber of phi meets the LC centers of F in at most one point. But okay, so here, I mean, the picture is, well, so here's, X, here's Y. We have some point here, and then our fiber is going to be this tree of rational curves, and it's going to meet, some LC center. In at most one point, but we see then this implies there must be some A1 sitting along in the fiber. But so there exists an A1 sitting in the fiber over, so we'll call this a little point Y over Y. Okay. And that concludes what we're doing here. Okay, so we've produced our A1 as we wanted. Okay, so I have 5 minutes. Maybe I won't have time to prove it, but I just want to explain another application, which I think is also pretty interesting, and I think is relevant for studying all this stuff in the log canonical case. But it's an application to the existence of subparatrices of singularities. So we know by work of Cano and Cerveau, so that non-diagonal singularities always admit subparatrices. And in general, if in general a dicritical singularity will have no subparatrices. So a question which I think is a bit curious is, well, under what conditions can we guarantee that a diacritical foliation singularity emits a separatrix? And so we're able to prove the following, which is a bit curious to me. So again, this is with Roberto. Is we can show that. So let F be a germ of a log canonical foliation singularity. A canonical singularity on C3, or a germ of C3. Then F admits a separatrix. I don't know. I think this is a bit of a surprising result, because in general, log canonical foliation singularities, they're dicritical. But here, we can actually see that somehow there's something nice about them. They're somehow kind of well behaved. So maybe I'll finish up then by asking a question which seems kind of natural to me, but I don't know the answer to. Maybe I'll also make a quick remark, is that this still holds true if the underlying space is KLT, but not if it's log canonical. So somehow you can prove somehow a more singular version of this. But so here's a question that I have that I mean maybe I should have to, but I don't, is that do log canonical singularities, so I mean any rank, any dimension, and any dimension admit separatrices? So like I said, I think this is a kind of interesting question. I think this sort of ingredient is probably really important if we want to try and, I think it's of independent interest, but I also think that we need to understand these things better if we want to run the MMP in the class of log canonical foliations. Okay, so maybe I'll end it there, and thanks for your attention.